Okay, should be going. No, yep. All right. So thank you for this. It is kind of nasty here. It kind of stopped now, but I know it's going to pick back up. But the plan today is to go through a dynamometer, and we're going to analyze it kind of together. Okay. I'll explain what the purposes are for it and some things behind, a little background behind it. Um, then you'll do an Excel and you'll make some plots, and then those will be due next week. And then I'll bring this into class next week so you can check it out. But I'll bring my camera over so you can see kind of what's going on. Um, Over here, so I've shared this screen, and this is just some background, okay, an overview on this. So let me zoom in. So this is the front side of, say, one dynamometer, and this focuses on just looking at motor characteristics. Okay, so you can look at torque, you can look at RPMs of the motor, you can look at power in and the output power from the motor. Okay, why is this important? Well, if you're trying to test motors, the easiest way is to have a tabletop setup that you can just pop one in, test the performance, and then um, get what you need, and you could do it right there in place instead of putting it in, for example, like some sort of car and then going outside. Okay, so this is the front view. Hold on one second. Okay, so you have this is the dynamometer. This is the back side. So you have the circuitry. You'll have this flywheel. Now, inside that housing is something like this. It's a flywheel, has a certain thickness, has a certain diameter, and what you're doing is you're applying a load on that motor. So this is called an inertia dynamometer because we're going to accelerate from zero up, and it's going to accelerate this flywheel to a certain point where it's going to be at constant speed, and we can then analyze that inertia or that increase and look at torque and power that way. Okay, so these are flywheels, and they have a characteristic called mass moment of inertia. Okay, you could actually change and make and have smaller flywheels in that housing. What is the importance of having different sizes? Well, it depends on the motor. So if you have a small diameter one that maybe is thinner, then you could use smaller motors. The smaller motor wouldn't be able to handle something like this probably because this is too big, too much of a load, and it just won't um, perform to where you need it to be. Okay, so that's why we have different flywheels that we can put in the housing. You also notice that this one has a one black marker and this one has four black markers. Okay, these markings indicate like a timestamp. So as this spins around, okay, there's a sensor in this electronic. It's like an optical sensor that will indicate when it's in the white and when it's black. And what will happen is that sensor will read a voltage of 0 when it's white, and then it will jump up to maybe 4 or 5 volts when it hits the black. Okay. So as this spins around, and if you count the number of times it spikes up, okay, and say 1 second, you can convert that count into what we call RPMs. Okay. So once we know the RPMs, we can figure out other characteristics of that motor. Okay, so you have um, the flywheel, you have different flywheels, which represent different loads on the motor. Okay, so this is just like a DC small motor. Okay, now what I have on my tabletop here, and I'll show you here in a minute, and I'll actually run it and show you, is a chassis dyno that we can put an RC car on. It's a small scale, and we actually have a big dynamometer in the auto lab. Maybe one day I'll see if Brandon can operate it for us. But that tests the performance of an automobile, the power, the speed, and you can actually swap out different components to see the performance of that automobile. This is the same thing, but it's just small scale, so you understand the fundamentals. There's a lot of companies that actually um, use or create their own dynamometer, and that's why I'm showing you this. When we went to Briggs and Stratton, they make lawnmowers, and they actually have two homemade dynamometers that they put their lawnmowers on, and they can test. So if they, and again, this is another reason to have them, is you can put a lawnmower on it and you can keep it there all winter because you can't go outside in the winter and mow. And you can change a part, you can change different batteries if it's electric, and test the performance of that. So knowing the fundamentals is important, and it also kind of brings back conservation of energy, some dynamics, some fluids, some thermo, I think it's a really unique thing that is important for you guys to know. So in a minute, I'll switch over. I'll move my camera over here so you can see the dyno. I'll operate it. Okay. Now in this lab manual document, I have variables, descriptions, and the units just for reference for you. So if I scroll down, let me zoom out some. This is an example performance curve that you would get from this dynamometer, okay? You could have electric power, which is your power in. So we're gonna have, where'd it go? We have some sort of power, which this is a battery, okay? This is what you call a lithium polymer battery, a LiPo, because it actually has like two plugs here. This plug right here, the white one, this goes to each one of the cells inside here. And then this is your actual main connector. So LiPos have different types of cells or different number of cells, and you want to charge each cell correctly. So this is a lithium polymer. And then the one I'm going to test with, I'll pull it off here. Oh. This one is a nickel metal hydrate battery. So if we know electric power, which is your power in, if you know the voltage and you know the current, you can then figure out your electric power in, right? That electric power in goes to the motor, and then that motor has a shaft, and that is your mechanical power, that's your output power, okay? And not only are you going to get mechanical power out, but you're going to get heat, right, going out. So you got heat release. So that's kind of included in the efficiency. So the efficiency is your output power over your input power. So your mechanical power over your electric power. And your efficiency is never going to be higher than one. Typically in DC motors or these types of motors, 50% is actually pretty good, okay? Because those are just not very efficient at getting your electric power to the output power. So we have also torque. Torque is kind of a representative of how much power you also have. I'll go through that a little bit later. But then you also have this RPM graph. So what I'm going to do is I'm going to keep going through this, and then we're going to run this dynamometer. We're going to get data, and there's going to be an Excel sheet, and we're going to take information out of that. You're going to plot a curve. Okay, so that's the goal of this, is to create a spreadsheet and graphs. Questions so far? Is it making sense? You following along?
Yep, all good.
Okay. The next section here goes through, okay, what's angular velocity? Angular velocity is so now you have something spinning. So we relate that to omega, which is angular velocity, is how fast this thing is spinning, and that's radians per second. And that's kind of the same thing as your RPMs. It's just a conversion, okay? Electric power, I kind of went through that already, volts times current. And just to be aware, depending on the amount of current that's going through, you want to make sure your wire diameter is correct. Otherwise, it's going to get hot because you're forcing a lot of electrons. You're trying to force them fast through a skinny wire, and it's just not going to work, okay? So I put some fun facts in here. I think up here, I think we get about 25 amps with this RC car that I'll show you here in a second, which is actually quite a bit. Mechanical power is your shaft output. Your torque is your rotating force created by the motor shaft, okay? Why do we look at torque? Well, a lot of times in my hobby, we have crawler tracks or crawler vehicles. They're slower, much slower, but they have a lot of torque, meaning they could actually like climb or crawl over a rock, and they have that much torque to get over that rock, where if you took like a short course truck or a monster truck, it wouldn't do that, because the torque isn't as high. Efficiency, I talked about that, never going to be higher than 1. It's always going to be lower, and it's output over input, okay? I talked about this briefly, energy. So energy in equals energy out. So if we have electric power in, then that's going to equal your heat transfer out and your shaft power out, okay? So down here, again, electric power in, voltage times current. Your output power is your torque times omega, okay? And then I give you these equations, which you will use in the table. So torque is your moment of inertia of the flywheel, I, times alpha. Alpha is your angular acceleration. So how fast is this thing accelerating? Okay. And then N is your gear ratio. Okay, and that's going to be N squared. The gear ratio that we're going to look at is actually going to be the tire diameter of this RC car to this long drum that I'll show you here in a second, okay? I believe it's going to be 0.7 for this gear ratio. Tell you how to find alpha. It's just a change in omega over T. That should actually be, let me fix that right now. That should be this. Oh, I didn't like it. Let me change that. If you want, you can change it too. Oh, it's not letting me do that, huh? Well, I'll have to symbol. Huh, it won't let me. Okay, I can fix that, but that's omega. Okay. Let's go back. So this moment of inertia of the flywheel kind of describes how this mass is distributed out this radius, okay? I don't have an experiment to calculate that yet, but I'm going to. What I want to do is 3D print a part right here with a pulley where we can put a string. And what you do is you put a mass on it and you drop it. And then this spins slowly and you time how long it takes to drop. And you can do some other calculations to find this mass moment of inertia. What I'm going to do is we're just going to find it online on their website that makes this dynamometer. Okay. I believe it's like 2,000 kilograms millimeter squared, but we'll just use that number right now. Okay. All right. Angular velocity. That is 2 pi times n dot. N dot is your RPMs over 60. And then the revolutions per minute comes from those counts. Okay. So if you're going to take 60 seconds over 1 minute, that's just conversion, because our delta T is going to be in seconds. Okay. This is the counts, and then this is the number of markers. Okay. So if we spin this and we count, say in 1 second, there's 16 markers and there's 1, then if you had 4 and you did it in 1 second, it'd be 4 times 16. Okay. So you'd have a lot more counts in 1 second if you have more markers. Okay. And then it's going to be times your gear ratio, because we want to know how fast these tires are spinning, not the drum. Okay. Let's keep going. Efficiency, I talked about that. Output over input. And then you can actually use the RPMs and the circumference of the tire, and you divide that by 60, then you can figure out your linear speed of that object. Okay. And then here is an example of what those counts would look like. Okay. So you see how it spikes up? So between 2.5 and 4, let me zoom right in here. We'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'd have 10 counts in about what, 1.5 seconds. Okay. So you could figure out what the RPM would be at that time interval. Okay. So what we're going to do is I'm going to bring the camera over here and hopefully you can see it. I might, let's see if I can bring it over here now. Let me switch the camera. Surface camera rear. And I can pull this. Okay, good. I can unplug it for now. All right. So can I highlight myself for everybody? Spotlight for everyone. There we go. All right. So figure out why the camera angle, it's backwards. Oh, that's weird. I move left and it moves right. So I got to figure out how to do this. I don't know why it's doing that. Why is it backwards? Maybe it's the spotlight? No. What the? Is it upside down? Okay. Sorry. I'm probably making you dizzy right now. I can keep sharing. So you can still see my screen. God,
Yep.
why is this so hard? It's like totally backwards. Got to figure out why it's doing this because I can't get it through my head here. Okay, well, I'll do this right here for now. And I'll try to do my phone here in a second. So here's the RC car, here is your tire. And then right here that it's touching, that's your drum, okay? So as this spins, it's actually spinning this flywheel here that's inside the housing. And there's actually gears and a belt right here. So here's the hub. Here is your belt system. If I can figure it out here. And then these pulleys are actually the same diameter from this to attach to the flywheel. So as we spin this, okay, we can figure things out. So how do we do this? Well, let me see if I can first change to the software. All right. So you can still see my screen. This is the Dyno software from the company. And I plug in the battery. It should turn on. Let me disconnect and connect. No, let me try restarting it. Should give us a voltage here. Oh. I just tested this just before I left. Okay, so okay, connect. Why is it not connecting? Awesome. I literally 10 minutes before class checked it. Huh. Oh, there we go. Okay, finally. So here is the, so sorry, I don't understand why this is not working. Let me turn it off and on. Maybe it needs to be reset. Now the camera's not even working. Okay. So what we're going to do is I got to make sure this controller is on. And I'm going to run a manual test. I'm going to start logging. And I'm going to just hit the throttle, okay? So I have here the throttle. And you'll see a curve. Stop logging. So I pretty much hit the gas with the throttle. You had your wheel here. It turned this big drum. It then connected the belts, the pulleys on this backside, and then we're spinning the flywheel. And then all the electronics are actually converting. It's actually calculating the counts and calculating current in this case, RPMs, and voltage. Okay. So this is that chassis. Now let me switch the camera here. Put you back over here. Plug this back in. Okay. All right, mouse, where are you? There. Okay, so if we go back to the graph here, can I zoom out here? There we go. Okay. This actually shows, so the green, this line right here is voltage. So voltage is over here. So it's about what, almost 10 volts at the start. And then current is the pink, which is this line here. That's over here. That shoots up to almost 25 amps. Okay. And then we have RPM, which is this blue, and it goes almost up to 3,000 revolutions per minute. Okay. Now, inside, so the flywheel that I had in the housing is actually 124 millimeters. I think it's 10 millimeters thick, just like this one, but it's stainless steel. So it's a lot heavier. It has a different, it's a kind of a higher mass moment of inertia. And I put it on here because these RC cars kind of need a higher mass moment of inertia. Okay. If I put this in, this thing would just crank up and it would be hardly any load on that RC car. Okay. So this is a data set. And what we're going to do is we're going to export this. We're going to export test one. And I'm going to send this in Teams and I'll upload it. Okay. Test data mech 221. This would be Thursday. Downloads. Okay. So I'm going to send this into the chat and I'll upload it in Brightspace. Okay. So Thursday. Oh, you're fine, Chelsea. How was the career fair? Good.
Yeah, there were a lot of really good companies there. I got into plenty of conversations, many internship opportunities, so lots of stuff.
Great.
For sure.
Great. I'm hoping a lot of students were able to go. Was it busy? I hope.
Decently, yeah. There was quite a good turnout. I know at the very least Sam, who's actually right over in the same room, was at the career fair. We both kind of just got back from that.
Oh, yeah. That's totally fine. That's why I'm recording this.
Hi, Dr. Craig.
Missed a whole lot. Hi, Sam.
Yeah, we're kind of chilling in your classroom here, Neville South 111.
That's perfectly fine. It probably would have taken me 2.5, 3 hours today to get up there. So.
Oh yeah, I bet. Honestly, I'm a little scared to leave campus currently.
Yeah, drive safe. Plus,
yeah.
they canceled the engineering week. So hey, Daryl. Oh, you got that? Nice. Did you found the batteries then?
You found batteries on it, he asked?
Oh yeah.
Oh, awesome. Thanks, Daryl. Tell him thank you.
He said thanks.
All right, so I uploaded the Excel data in there. And then I'm going to post it into the Brightspace. I don't know. Hopefully I got the right one, but I'll put both data sets in here. All right. So in the meantime, while I'm doing this, what you need to do is you need to grab two things. You need to grab that data set that I just exported, which is in Teams, and open up this Excel sheet that is in Teams, OneNote, and Brightspace. It's called Excel Template Dyno. Let me know if you can't find it. Throw it in the chat if you're having issues. But I think I have it in the chat as well. Okay. So I'm going to put that here. Did I? Oh, yeah. So lab 3 should be in there. Let me click on this one. Content. Lab 3, good. Okay. I'm just putting all the data sets in the same spot.
Yeah, both of them are popping up on my end, so I know at the very least they're working for me.
Okay, great. Okay, good. Okay, so you're going to open up, so this Excel sheet. Now let me see if I can open up both. You can make sure you got these open, and I'll give you a few minutes. I'm going to turn this off. It's kind of loud here. And I'll just put this over here for now, and then I'll show you what you need to do. do here. Okay, so give everybody a few minutes to get those up. Just let me know in the chat if you got these two up. Okay. And again, I'll bring this in next week so you can take a look. And if you want, you can try it out. Just gonna grab a drink. Did everyone else have a chance to get to the career fair? Maybe. Okay. Is everyone good? Yes, I see you're good. Kaden, Alex.
Yep, I'm good.
Steve, Madeline. Okay. All right. Okay. Okay. So I'm just going to blow this one up first. So this is the one you're going to do first, or this is the one you're going to fill in. Okay. And make sure you have your heading at the top, right? I didn't put that in here. And then you're going to have this as your table. And then you're going to make, I believe, 4 graphs. Okay. Separate graphs. And it's going to be power in versus time, power out versus time, RPM versus time, and speed versus time. Okay. So I believe, I don't know if, what time did the data set? So probably 7. You see how in this graph, I didn't hit the throttle until probably 7 seconds. Okay. So what we're going to do is you can change this to 7. Okay. So change this first one to 7, and this would be 7.25. This would be 7.5. And then what? 8.75, 9, 9.25, 9.5, 9.75, 10, 10.25. And I'm gonna show you how to do a few of these, but I want you to keep going until let's do 14 seconds. Okay. So keep going all the way down like this, okay, to 14 seconds. All right. But you can do that after you start plugging some numbers in. Okay. Now, let's talk about something. So you see how I have time here is 7. I'll highlight, let's do red. And then this is 7.5. In between 7 seconds and 7.5, which is a delta T of 0.5, we're going to find the counts. Okay. And we're going to look at that data sheet that I just sent you. Okay. So you can actually put in 0.7 here. All right. And copy and paste this in these white spaces. Because this is the gear ratio. That is the ratio of the tire to the drum. Okay. I believe it might be the drum to the tire. The tire has a smaller diameter. I believe the tire diameter, which you're going to need for circumference, we'll do that in a second, is 88 millimeters. Okay. So this is the gear ratio between the tire and the drum. And this one you can put in, let me show you how to find that. I'm going to go to Mini Pro, Dyno, right here. Let me bring this over here. So this is this company, and I can send you the link and put it in the chat. So if you go to products, you can go to dynamometers, and they have a whole bunch of different kinds. Okay. As you notice, here's the chassis dyno. I am actually working with this company. I'm actually writing the manual for an inertia dyno for them. And our school, like almost a decade ago, was the first to buy their first like motor dyno. Okay. And the chassis dyno. So this is like their first one they pretty much produced. We ordered it and sent it here because there was a capstone group working on an electric skateboard, and we wanted to know the performance of that, and measure the motors. So this is the site. So we're going to go to products. We're going to go to flywheels, and here's all the different flywheels. Like, look at this yellow aluminum. This is 3 millimeter, all right, thickness and 90 diameter. So I have the blue one here. I have the, I don't know if I actually have the steel one. Typically that's always out of stock for some reason. I have the aluminum, red one, okay? And then the steel one is in the car right there. So if I click it, look at that, it's $430. It's crazy expensive, but it's been machined and it's leveled. Down here in description, it tells you the diameter, the thickness, the shaft diameter, and then it gives you the inertia of the flywheel. So we're going to use this right here. Okay. So you can, I'm going to copy this, go back to the Excel sheet, and you're going to put 2002.18, but you're going to multiply by 1/1000 squared because, should be caret 2, because it's the unit was millimeters, so you should get something pretty small, okay, because it's kilogram per meter squared. Then if you want, you can copy and paste this down because that doesn't change, correct? All right, and again, you're going to go down, you're going to basically copy and paste like these and go all the way down to 14 seconds when you get there. Okay, so what we got to do now is we're going to look for, let me put this as light blue, we're going to look for counts, and I want you to look for volts and current. And everything else, RPMs, circumference, I'll do it here in a second. Velocity, we'll do in a second. All of these then are equations, okay? So make sure you save that. So let's go to the data. It's here. So if you have this, you should have this Excel open. And what you're going to look at is voltage, current. So I'll highlight those blue, as well as time and pulse counts. Okay. Everything else in this particular lab, you don't need to look at. Okay. They actually give you all of this information in this Excel. But I don't want you just simply just to take that and use it. I want to make sure you understand the process, because a lot of the times in companies, they don't buy these, they make their own. So you should know how to do it. So what we're going to do is, if you scroll down, you should notice that the counts, see how they're all 0, and then at 7.8 seconds, it's 2. Okay. That means that's where we started. So what we're going to do is we need to look at the counts between 7 and 7.5, right? So what I like to do is I like to highlight these, and we'll go to here. So 7.5, actually, let's go right before it. I like to highlight these. So let's do orange. Okay. So there's no counts, which is fine. Okay. Next one, We're going to go from 7.5 to 8, which is here. And then I'll highlight that a different color, to green. Everyone okay? Everyone following? Questions? Okay. So between 7 and 7.5, there's no counts. So let's go back to this graph and put 0. Oh, did I add that wrong? Oh, I did. Huh? That should be what? 7.75? And then 8. I don't know why I did that. I can't count. 8.5, 8.75, 9. Anybody else catch that? Did I skip something? Now let's look between 7.5 and 8, which is, again, we're looking at the counts in 0.5 seconds. So if I go back to this graph, between 7.5 and 8, how many are, you count all of these, how many are there? 5? See that? So we're going to put 5 right here. And I'm just highlighting these. You don't need to, but I just want to make sure you understand kind of what I'm doing at the same time. You can save it. Let's do one more to make sure. So let's go between 8. Let's do purple or magenta and 8.5. So if I go back to the data, between 8 and 8.5 right there, highlight those. So that's 4 plus 5. Sorry, that's 9, right? Plus 6, 15, plus 7, 22. That make sense? So that's going to be 22. So you need to do that. I want you to do that from 7 all the way down to 14 seconds. Okay? So you're counting the counts between 7 and 7.5, 7.5 to 8. Those are in increments of 0.5. Okay? Questions on this? Okay, now what we need to do next is you need to grab the volts and current, and I want you to grab them at this or close to this average time. So at 7.25, let's go to this one. So at 7.25, which is roughly, it's fine. You could do 7.2 or 7.35. It don't really matter. Actually, let's do 7.3. We're going to scoot back here. And the voltage is 9.3 and the current is 0. So go ahead and write that down. 9.3, oh my God, not 90, and 0. Then we're going to look at the current and voltage at 7.75. So 7.75, you can do 7.6. Oh, so again, 9.35, 7.75. Did I look that up right? Oh no, yeah, right here. Let's do this one right here. You can do either one. I don't really care as long as you're close. So 7.54 and 20.62. Okay. While you're filling those in, what Like, isn't that crazy to think when I hit that throttle, when you hit the gas on something, um, the voltage will drop and the current will go up. Okay, that's what happens. So the mini Baja or the Baja, when you do your electric, when you hit that gas pedal, this is the same trend that's going to happen. When you floor it, your voltage is going to drop, compensate for that increase in current. Let's do one more here, and then we'll kind of keep going. 8.25. Let's do 8.3. So 7.23 and 22.76. 7.23, and I can't remember off my head. 22.76. Boom. So so right now, those are the only data that I want you to get from that Excel sheet. Okay, does that make sense? But you're gonna get all the data from 7 down to 14 seconds. So you're like halfway there, right, or so. So you're gonna probably maybe end up down to here somewhere, right? So oh my gosh, let's copy and paste this a few times so you can get an idea. So this would be what, 9.5, 9.75, and 10, and then just keep going. Okay. Oh, no, no, don't copy and paste like that. Make sure you get it like this, because there's a reason why I did it like that.
So for this lab, we're
8.75.
literally only collecting the count voltage and amperes
Current.
here. Okay, current,
Yep,
yeah.
and the current. Yep. Oh, what happened was
Okay.
this? It was this number. Yep, 22.76. How did that get deleted? Oh. Okay. Yes. So you're gonna keep going all the way down to 14, and I only want you to get the counts, the volts, and the current from that. Yep. Okay. And again, we're picking a delta T. Okay. We're picking 0.5. Do you have to do 0.5? Nope. You could pick 0.25. You'd have just more data points. Okay. So now, if you notice, you see how I have this whole thing right here is white, and then it jumps down to here, white. So the white is where you're putting it in. The reason is because when you find like omega and then omega average, you're going to take these two values. I'm going to go through like this first white and probably the second one so you can get some data values here. Okay. But before I continue, any questions?
Please, sir,
Hmm?
can you remember the different graph?
Say that again.
Can you remember the different graph?
Can I remember the different graph? Can you
Yeah,
explain?
the different graphs that we have to do.
Oh, yes. What you're going to do is you're going to have power in versus time. You're going to have power out versus time, efficiency versus time, RPM, and speed. Yep. So they're right in this lab thing that I asked you to do.
All right, thanks, sir.
Okay. Yep. Okay. Other questions before I continue? Okay. So what I'm going to do is this Word file has the equations that you need, and we're going to do this RPM first. So what I'm going to do is just going to bring this to the other window, blow it up, and now let's do RPM here. RPM is equal to 60 divided by 1 times 1 divided by delta T, which you could click here. And then times your count divided by the number of markers, which is in this case 4, and then times this 0.7. I think you can see the equation up here. So what I'll do is hit enter and go back to it. So you should be able to see it right up there. Okay. Oh my gosh. So it's just like that equation. It's 60 over 1 divided by delta T, but I clicked on this cell. Multiplied by the counts, you click on this cell. Times or divided by the number of markers, because the flywheel, the stainless steel flywheel, actually has four black markers. Okay. And then I multiplied it by the gear ratio because I want to find out what the RPMs of the tire is. Okay. Or are. Everyone get that? So what you can do, watch this. If you see how I have my crosshairs like right here. If I left click and drag and let go, so I grab 2, I can then do the corners and go down, and it fills in every other spot. Let me do that again. Click on this cell, and my crosshairs are thick. I'm going to left click, drag down 2, and I'm going to take the corner. Now my crosshairs are kind of skinny black, and I'm going to drag, hold. I'm going to left click and hold and drag down and let go. And what I'll do is I'm going to keep these blue. I'll keep these green, and I'll keep the, oh my gosh, purple. Everyone get 0, 105, and 462? If you didn't, let me know.
Yeah, mine decided to try and fill in the gray ones too, which gave me a null value for those.
Yeah, you can go ahead and delete them, but if you click on this cell and you left click, hold, and drag down, then let go, you should be able to drag down and have it every other one. How we doing, everybody? Okay? Might as well make all of this. Doing good? Okay.
Yeah, no, it doesn't skip the cells for me, sadly. I get other
It
values,
doesn't?
so I still have the 105 and 462,
Okay.
but it
You can go
keeps
ahead and
trying to
just
fill that.
delete
Yeah,
those.
I'm
That's
just
fine.
gonna put that back.
Okay, let's do circumference. Can we do that? Caden, Maddie, Steve, you all right?
Yes, sir.
Okay. All right, let's do circumference.
Yeah.
So, okay, good. So that equals what? Pi d or 2 pi r. So do pi, open and close, times, it's going to be 88 divided by 1,000. Because it's 88 millimeters. That tire diameter is 88. Yeah, that's terrible. Look at that horrible format. Let's keep it like that. So it's just pi d. 88 millimeters is the tire diameter. And then, do you remember what the velocity equation was? That was, oh my gosh, that was circumference. So we're going to click, let's do parenthesis. This times RPMs, close parenthesis, divided by 60. And then I'm going to drag these both down. And that is horrible. Let's do 3 decimal places. So did I go too fast? You get that?
What was the velocity equation that you used?
Yep.
Sorry.
It's going to be the circumference. So I clicked on the circumference cell and I times it by the RPM cell. And then I divided by 60. So it's pretty cool how you can have, if you know your revolutions per minute and you know the circumference of that tire, you pretty much what you do is that circumference, right? You lay out in a linear line. And that's kind of the distance it went in that second. Okay, that's how they get velocity. And then we can highlight these and change oh, there we go. There. Okay, keep going.
Yes, sir. Can you put the formula of the speed?
Yep. So it's going to be linear speed. You're going to take, let me do this. Say equals. You're going to click, you're going to have open parenthesis. You're going to multiply by circumference. So you're going to multiply by the RPMs. Then you're going to close and divide by 60. Then you can drag those down. Is that good? You good now, Steve?
Yes, sir. Thanks.
Okay. Yep. All right, let's do power in. That's equal.
I did get a slightly different number for one of them. I'm wondering if I did something wrong.
How far off is it?
It's the velocity you have for the increment of 7.5. I have 0.483. However, for the next one,
fine.
I have 2.125.
Oh, that's okay. Don't worry
I
about
got the
that.
same.
Yep.
Yeah,
It's
I'm not
probably
quite sure why
it could
did
be.
that.
I don't know. I have no. Oh, I'm not sure. Don't worry. As long as it's close. I might have a different Excel that might round slightly different. All right. So power in is equal to the volts times the current. Right there. And you can drag those down. And I'm just going to paste those in. And let's keep that format. Let's keep that format. And this, so you can clearly see and let's go 2 decimal places. So we got the power in, and this is watts, 155 watts. Kind of crazy for this little battery, right? Okay, let's see, what's next? Omega, angular velocity. So that's going to say equals 2 times pi, open, close parenthesis, times your RPM divided by 60. So omega is 2 times pi times your RPM over 60. That converts it to radians per second. You're doing that. I'm just going to check. Everyone good?
Yep.
Good. All right.
Yep.
What's next? So hit enter. Let's drag this down. Okay, Chelsea, I'm just going to mute you. I
Oh,
hear.
shoot. Sorry.
No, that's fine. You're fine. Okay, let me just fix this. Okay, so that is your what? Angular. Now, while I'm doing this, how would you think you could find the average? So the average now is now in this section. So we're going to be looking here because they're going to be values that we need in between. Okay, and I'll do, we can do these two for right now. So the average omega is you're going to click the 11. So at that time, you're going to basically add this one and you're going to divide by 2. So it's the average between the two and hit enter. Okay. So I just averaged 11 and 0. And then you can, again, bring that down. Okay. You can, once you put numbers in, I'm just going to delete that because there's no numbers down below. Let me do green. And I don't know why I'm doing this because it's going to change, but that's fine. Questions on that? So that should be the average between this 48.3 and 11. Okay, alpha. That is how fast we're increasing in an angular. So you're going to take, it's going to be equals, parenthesis. You're going to take omega here, so 11, and you're going to subtract the top one, which is 0, close parenthesis, and you're going to divide by delta t, which is right here, 0.5. Sorry. Now you don't have to click 0.5 if you want to. You could just say divided by 0.5. But again, alpha is, I might as well do it here. Alpha is going to be equal to the omega here. Let me put a parenthesis. And you can drag it down. I'm just doing this. Subtract the one above, and you're going to divide by 0.5, which is your delta t. Everyone get that?
Yep.
Now we're on the torque. Okay, good. Okay, so let's do torque. So that equals, parenthesis, that is your I value, which is right here. So D4 times alpha, which is N5, close parenthesis, divided by N, which is C4, and that's going to be squared. You click enter. So again, torque is I times alpha over N squared. And we can close, we can make those look a little pretty. And I'm just going to drag this down here. Getting there, right? Three more left. We got the torque. Now the P in average, I'm doing this because we're going to do efficiency later. So you're going to take your average power here, and you're going to average it above. And basically add them and divide by 2. So again, P average, as I'm just averaging these 2 values to get an average value, okay? Okay, good. And then P out equals, that's the torque that we calculated, times omega, which would be omega average. Okay, that's why we did average. And then you can click enter. So let me, I don't know why I have this thing in the way. Got all these tools. My phone doesn't like to work. Oh, come on. Figure that out later. Okay, so we got questions as I'm finishing this. We can do efficiency, which is equal to out divided by in. And do you want to do, let's do percentage. So do out and in times 100, right? So 6%. As long as you know what you did, it doesn't matter. I don't really care if you do the value or not, because you'll get it. Let's do that to right there. So we just did pretty much 2 sets. So really what you need to do is you need to finish this all the way down to 14 seconds. Then pretty much you can drag these and drag them down, right? You should get to a point, and I'll come back. Do you see how the RPMs? I do time. Yeah, let's do speed. Speed is blue. So the speed reaches a constant value around 33 or so miles. This is kilometers per hour, which I think is probably 20 meters per second. What's going to happen to alpha? Can someone tell me? What happens to this term as you approach a constant velocity? Are you accelerating anymore? No. So that should pretty much go to 0 towards the end.
I was gonna say, doesn't that zero out after a certain point?
It will.
Yeah.
So that means what's going to happen is there's no more torque, right? Because this inertia dyno is measuring that increase in acceleration. Okay. So what I like to do a lot is I'll take this into local middle schools and high schools, and we'll run the data, but we'll only do RPMs and speed, because we pop out, we'll put a different pinion in. So if you put a bigger pinion in, you can actually increase your speed. So I show them, hey, let's put a bigger gear in. What's going to happen? They don't know. So I hit the gas, run, and look at it. And they're like, oh, okay. So a bigger pinion, you're going to go faster. So that's what I like to do to demonstrate this stuff, to make sure you understand what's happening and why we do certain things. Did everyone get this? Does it make sense? Go ahead, Steve.
Can you put the formula of P out?
Yep. So P out is going to be the torque So tau cell, which is 0.5, and you're going to multiply it by M5. So again, all of these equations are in the lab manual if you ever get stuck and you want to look, okay? So output power, torque, alpha, they're all in that.
I gotta print that
Word
out at
lab.
some point.
Yeah. So the goal, if you notice, the goal for this lab, you should make a binder and make tabs and label it. Don't label it like lab 1, just label it. Well, I guess lab 1 you can because it's just format, right? But lab 2, you could actually put in there stress strain curves, right? Lab 3, dynamometer. Next week and the week after, we're going to look at temperature sensors, and you're going to write a full lab report, and I'm going to help you with that. Okay. So that'll be temperature sensors.
So basically, like, kind of creating a small portfolio of the class.
Exactly.
Okay.
Yep. I would. That's what I would do. That's what I'm trying to get you to do. So we're going to do temperature sensors. Then we're going to do hydrostatic forces before break. Then after break, we're going to go and do tensile stress, shear stress, the impact, torsion, and cold drawn, all of the stuff that I showed you before in lab. Okay. So Steve, you got torque or no power out? Is that what you were looking at? Yeah. Did you
Yep.
get efficiency?
Yep, sir.
Okay. So this is actually, I think I did this better today. Went through this instead of jumping in, but on Tuesday, I just showed them how to do it and then let them do it. But I think I like this better because now you know exactly what to do. But the rest you can get off now. I can stay here, but pretty much you just need to finish this and then make the plots. Okay. Does that make sense? What you need to do?
Yep, makes sense.
Okay. And then if you're ever at a job place and you need to make a dynamometer, you have all the basic stuff. Maddie, were you going to say something?
Just thank you. And I'll
Yeah.
see you next week.
Yes, sounds good. Yes, thank you, everyone. I'll just stop recording because I don't think we need to record anymore. But if you want to go, you're free to go.
Yeah, I'll see you in like a couple